how's everyone doing?
Good.
Glad to hear.
How are you doing?
Sleepy, but that's my standard answer on Mondays.
Oh, yeah, I found that.
Feels like there's too many things to do and not enough time, which is also my standard answer. So let me think of a different one. I'm feeling good about the weather.
Okay.
I like.
It's supposed to get really cold this week.
Oh, okay. I actually finally turned the heat on in my house. All right. Any questions, concerns, etc. from you guys before we get started today? Yes.
The questions that we started last class that we had to like leave in the middle of, are we gonna finish? Are we gonna go over that second part again since we had to like rush out of here early?
Yeah.
Like we did the second question, but we only found like the force of gravity, and then when we were trying to find the second part to answer the question, we were like.
This question you're talking about? Okay, yeah.
Let's about the velocity one and the bottom, like we had done the first one.
Right. So yeah, let's look back over this again. Last time we were looking at how gravity acts as a centripetal force in space, and also the formula that lets us calculate gravity in space. We call that the universal law of gravitation, and it says that any two objects with mass will exert a force of gravity on each other based on those masses and how far apart they are. So that again includes pretty much everything in space. Once an object gets to be the size of a moon or a planet, it starts creating noticeable levels of gravity, and that gravity can act as a centripetal force. So we looked at that formula, and we're kind of comparing it to the centripetal force formula. Since gravity can act as a centripetal force, in those scenarios, you can actually set these two formulas equal to one another. So last time, as we were talking about force of gravity, we calculated the force of gravity between several different things. That includes between the Earth and the Moon. That calculation should be in your notes, and it should look something like 6.67 times 10 to the negative 11th times the mass of the Earth, 5.98 times 10 to the 24th, times the mass of the Moon, 7.36 times 10 to the 22nd, all over the distance between the two objects squared, because r is the distance between the two. That does form the radius of a giant circle. So we don't cut the number in half, but we do have to convert it to meters, though. So the Moon and the Earth are about this many kilometers apart. We convert that to meters, we multiply it by 1,000. So we get 384 million meters, and that gets squared. When using this formula, there's typically some very big numbers involved, so make sure that you are properly and carefully inputting them into your calculator to avoid any issues. To do this one right, I believe the answer for the force of gravity between the Earth and the Moon came out to be 1.99 times 10 to the 20th newtons. Is that correct? So that is the force that both of these objects exert upon each other. The Earth pulls on the Moon, but likewise the Moon does pull on the Earth with the same amount of force in the opposite direction because of Newton's third law. However, the Earth is so big that that force does not cause the Earth to move. It does cause our oceans to move, but thankfully not the core of the planet. Now, that force is capable of acting as a centripetal force. And we know that the force of gravity from the Earth on the Moon does this because the Moon orbits the Earth. For the Moon to move in a circle around the Earth, some centripetal force has to be acting on it, and some real, tangible force always has to play the part of centripetal force. Centripetal force is not its own unique thing. Something has to play the role of centripetal force, like a part in a movie. And in this case, the actor playing centripetal force is the force of gravity. So that means that centripetal force is the force of gravity, and we can set these things equal to each other, which helps us to describe some more aspects of the Moon's orbit. So I'm going to physically write down the formulas for each set equal to each other. Force of gravity is gmm over r squared. Centripetal force is mass times centripetal acceleration. That said, centripetal acceleration has its own formulas, so I'm going to plug those in for AC. First up is AC can equal v squared over r, and furthermore, it can also equal omega squared times r. So these are both the centripetal force formula, just different forms depending on linear or rotational. And they are both equal to the gravity from the Earth on the moon, since that is what's causing the moon to accelerate centripetally. And we can use this fact, we can set them equal to each other and utilize that relationship in order to determine how fast the moon is moving, or how fast it would need to be moving in order to orbit the Earth at that distance. Feel good so far? Or memory refreshed? So, this force, gravitational force between the Earth and the Moon, is acting as a centripetal force. We found it with gmm over r squared. So I'm just going to take this number, bring it all the way back over here, and plug it in for that force of gravity. So we already worked all this out, so we can just put that number straight in over here. So that is the force of gravity, and it's going to act as a centripetal force. So just working down, substituting one line at a time. Centripetal force, mass times centripetal acceleration. That is a factor of its current velocity, so we can use this to try to figure out how fast the moon needs to move to make this happen. That's because when something is orbiting something else, you have to have a very specific balance of the value of the force, the distance it's rotating at, and also its current speed. All orbits have a very specific balance of those things, and if one of them isn't exactly right, something goes into chaos. The moon has to be moving at a very specific speed to orbit us at that correct distance. If its speed changes, likely the distance the Earth is from the moon will also change. If it speeds up, it has a tendency to drift away from us. So, the velocity matters in determining how that centripetal force affects it. So, we can use this relationship, the fact that force of gravity is acting as centripetal force, try to figure out what that speed is for it to orbit at this radius. I'm going to point out, one, these are the same r. They both refer to how far apart the two objects are. For gravity's case, it's the distance between their centers of mass, talking about that being the center of the gravitational effect and the distance between their centers. On the centripetal force side, r is the radius of rotation, and the moon is that distance away from the Earth, and it stays at that distance as it rotates around. So on both sides of this, it's the same r, it's the same number. So the r that we used over there is the same r that we're going to use over here. Now, if our goal is to solve for velocity, we now have to figure out what to use for mass. Weird thing is, we've got two objects here. We got the moon and the Earth. And we know both of their masses. The question is, which one do we plug in here? Moon. Very good. Why is it moon? I hear you guys muttering it. That's all right. Yeah, the moon is the object that is doing the centripetal motion. The moon is the object that is undergoing a centripetal acceleration. The v squared over r is the centripetal acceleration, and it's being multiplied by the moon's mass, since the moon is the thing that is centripetally accelerating. The moon is doing the orbiting around the Earth. The Earth isn't rotating, the moon is. So for that reason, the moon's mass needs to go here. And that is going to be generally true in any orbit type question. I'll elaborate on that in a sec. So So the moon's mass will go in here, the Earth's mass doesn't need to get used again. And now we can solve for the velocity of the moon. Any questions arriving at this point of making these conclusions? All right. Now, if you put this into your calculator correctly, work it out right, that linear speed should be 1,018 meters per second. This means that the moon is moving about 3 times the speed of sound. The moon is booking it through space. And it needs to be moving at that speed in order for it to keep orbiting at the same distance from us. And we want the moon to stay that distance from us, because if it got any closer or any further away, its effect on our tides would change, and that would mess up the entire planet. Yes?
One of the homework questions like this is like 2 things and then there's something in the middle.
Yes.
And it's asking about like the force exerted, I guess, by that thing in the middle.
I thought it was by the, what is the net force on it? On the thing in the middle? The net force on it.
Yeah,
Is that right?
on it, yes, not exerted by it. Like, would you just solve for both of them and then subtract them?
Yes.
Okay.
Because if you have 3 objects, and it's asking about the net force of gravity on the middle one from the 2 on the sides, you would need to figure out the force of gravity from A on B, and also the force of gravity from C on B. And since those 2 forces oppose each other, you'd subtract them from each other.
After.
Yeah, please continue to ask questions about it.
Okay. Thank you.
Oh. So backtrack slightly. How do you guys feel about this one? Okay. Excuse me. Now, this interaction right here, force of gravity equals force centripetal, that is the key to understanding orbit, an orbit type question. And real quick, I'm gonna point something out about that you can put in your notes. When an object is orbiting something else in space, the key to that scenario, the trick to understanding what's going to happen in that sort of a math question, is remembering force of gravity is acting as a centripetal force. That is true for any orbit type question on your homework or on, say, the upcoming test 2.
So they're always equal to each other?
Yes. If something is orbiting something else in space because of gravity, force of gravity is acting as a centripetal force, and a decent chunk of the points that I would give for such a test question is just writing and remembering this. This is the key to any orbit type question. Satellite orbiting Earth, moon orbiting Earth, meteor orbiting Earth, Earth orbiting sun. If the question has anything to do with something like that, this is your starting point. And the next thing to fill in after that would be filling in the equations for each of these 2 things. Remembering that there's 2 different forms for centripetal force. You just pick which one based on if you want to know V or omega. So this is how you tackle an orbit type question. So a few of those on the homework. There's going to be one of them on test 2 and one of them on the final exam. That also means there will be at least one of them on the practice test and the practice exam. I'll note again, it's the same R on both sides, so sometimes that might cancel out in an interesting way. I'll also note that this M is a counterpart to one of these M's. This M is always the orbiting object. which actually means it would cancel out with its counterpart on the other side. How does orbit sound for right now? Okay. We can keep I plan to keep practicing orbit, and again, there will be practice questions for it for upcoming test 2 and eventually the final exam. Now, with this said, the main thing that I want to do today is begin Chapter 8, which is just our second week of rotation. The fact that it's called Chapter 8 is just a textbook homework designation. So it's still rotation. We're not doing anything hugely new. But I want to begin what is officially called Chapter 8 because lab this week is about a new concept called torque, and I want to make sure you've all seen it before some of you do lab today or tomorrow. So does that sound fair? Any objections before moving on? All right. So, Chapter 8 is still rotation. We're still talking about spinning things, so we can still talk about orbit as well. That's not great. My computer's doing a thing. Let's hope this doesn't mess us up. It messed us up. Hold on. My computer's being weird. Sorry, guys. Bless you. All right, well, while this is reloading itself, Chapter 8 is going to be about additional rotational concepts. Again, we're continuing straight on. It's not really all new stuff. And Chapter 8 is going to be about these additional angular and linear relationships just beneath the last ones we talked about. So Chapter 7 was about introducing these angular and linear relationships. Chapter 8 is continuing that and looking at these next batch of comparisons further down. So, rotation 2. I mentioned that pretty much everything related to linear motion has an angular counterpart, and that is what we're going to be spending the week talking about. We've already looked at the motion concepts, straight up linear motion descriptions, displacement, velocity, acceleration. But most of the things we've covered have something to do with motion. Force causes motion, momentum is directly tied in with velocity, kinetic energy involves velocity. Most things that we've discussed somehow connect to motion. And if something can move linearly, and there's a physics concept related to it, odds are, it turns out, there is an angular counterpart to that thing. Which just means that there's a way to describe that concept rotationally instead of just linearly. And the thing that we're going to be looking at today is torque. Torque is the angular counterpart of force. Linear force up till this point has caused linear acceleration, correct? If you push something in a straight line, if you exert force on mass, you're going to cause that object to accelerate in a straight line, correct? Is that generally true of how you understand reality? That makes normal force a linear concept. Linear force causes linear acceleration. That means that if you want to use force to make something spin instead of move in a straight line, you have to convert it into torque first. Now, who's heard the word torque before, even if not in science class? Okay, about half. Now, once again, we have the disembodied bike wheel of science. And there's several different ways that I can exert force on this thing to try to make it move. Right now, I'm just holding on to, the central axle of the wheel. And if I exert force here on this axle, I'm going to cause linear motion. Linear force on the axle is going to cause linear acceleration. And that's how we're used to it, right? That's because the force I'm exerting is basically acting on the tire's center of mass. If I exert linear force directly on the object's center of mass, it causes linear acceleration. And that's what Newton's second law says. Force on just the mass directly is linear acceleration, or causes linear acceleration. But there's another way that force can be applied to this wheel, because we know the wheel can spin, right? And so if instead of applying force on the axle, what if I apply force here? Now the wheel's spinning. I'm exerting force and the wheel is spinning. What's different about exerting it here versus here? There are angles involved, yes. I thought I heard something else. The key difference is that if I'm exerting force here, I'm exerting that force on the wheel's center of mass directly. But if I exert it here, I'm exerting that force some distance away from its center of mass, away from this axle of rotation. Torque is caused by exerting force at a radius away from a pivot point. And that brings me to the formula for torque. This symbol right here, it's basically a T, but it's technically a Greek letter tau, specifically lowercase tau. Just for a little bit of context, I can have it. All my mothers are sad. Uppercase tau looks like a cross between the T and maybe an umbrella. Lowercase tau is like lowercase t, but fancier. Well, if I was to write a normal English T, it would look like that. Well, fun fact, within physics, all three of these letters are used for different things. Lowercase English t is time. Uppercase English t is period of oscillation, which we'll talk about in a few weeks. And lowercase tau is torque. So when I say tau, I'm likely just referring to torque. And again, physics ran out of letters a long time ago. There's too many things that start with T. Yes?
So torque would cause, like the omega, I guess it is the W that we learned about. Because I thought that was angular velocity, or angular speed.
Omega is angular speed, correct.
This is what causes it, right?
Yes.
Okay.
Linear force causes linear acceleration. Therefore, if we think about it angularly, torque causes angular acceleration. So linear acceleration is A, angular acceleration, its counterpart is alpha. Now, these cause changes in velocity. So A causes delta V and alpha causes delta omega.
Okay.
So you were getting there, you're right.
Okay.
Because of torque, things spin. And if they are spinning, they have an omega. I'm going to talk about what I means later. Trust me, I'm putting it off for a reason. But since torque is the angular counterpart of force, torque causes angular acceleration. And the way that you generate torque is with normal force. If you use a force, you can use that force to generate torque. The way that you do that is you exert that force at a radius away from a point of rotation. When I do that with the tire, If I want to make the tire spin, I have to grab it on its edge. And that edge is a literal radius away from the axle. So the force I'm exerting is acting physically some number of centimeters away from that pivot point. And so the R in that formula would be this physical radius, the radius of the wheel. And you have to exert a force at a radius away from the fulcrum in order for it to be torque. If I exert the force on the fulcrum, it's not torque. It's just going to cause linear acceleration. It's just force. It has to be at some distance away. Now, the weird thing about torque is you have used it every single day of your life that you have ever opened a door, and you might not have ever thought about it. Please look over here at the old-fashioned wooden door of science. This is an object designed to use torque because it has hinges. It specifically has an axis of rotation, and we open and close it along that axis. Now, where do you place your hand to exert force on this door to open or close it?
On the other end, on the opposite end of the hinges.
Opposite end of the hinges. That's usually why the doorknob lives here and not here. Because even if you're not using the doorknob, you might grab it on this far edge, right? And it takes very little effort to make the door move if you're exerting force right on this side. That's because this edge is a significant radius away from the axis of rotation, from the hinges. And in general, the greater the distance you exert your force from the hinge, the more torque you generate. And the more torque you generate, the easier it is to make something spin, because torque causes angular acceleration. Torque causes spin. So you just know conceptually, I want as much of a radius from the hinge as possible, so I put my hand here. I challenge you to test this. Instead, put your hand here. Am I causing any rotation? Very little. This is very difficult, and it's not worth it. If I apply the force on the hinge, the radius is teeny tiny. So I get very little torque for my effort. So once again, the formula says, you exert the force some distance away from a site of rotation, like a fulcrum or a hinge. You generate torque. The greater the force you use, the more torque you get. And the bigger that distance is from the rotation spot, the more torque you get. Again, that's why you use the side of the door furthest away from the hinge. And you know this conceptually. Even if there wasn't a doorknob, I doubt any of you would instinctively try to apply force on the hinge. Does that sound right? This is one of those physics concepts that people actually have a pretty good subconscious understanding of. Because there is way more applications of torque in common, normal American life than just doors. It turns out pretty much every tool that humans have invented and use regularly somehow involves torque. For example, wrenches. The purpose of a wrench is to make something spin, right? You want to take this bolt and physically rotate it so it screws into whatever it's attached to. Is that correct? If you want something to spin, you need to exert torque on it to cause angular acceleration. And the tool we use to rotate bolts is a wrench, which conveniently has a long handle of length R. And the longer the handle, the greater the distance you can exert that force away from the bolt, the more torque you generate. You ever noticed how it's usually a pain to just try to grab the bolt with your fingers and turn it? That's because that would be a very teeny tiny applied radius. If I just took my hands on this directly, the radius of rotation would just be the width of the bolt. But if I use the wrench, The radius is the length of the wrench. Much bigger, generate more torque. In this particular case, how much torque do we generate if we apply a 12 Newton force at the end of this 1 meter long wrench? 12. What would the unit of torque be? Newtons times meters. Very good. I'll back up real quick to show this. Torque is measured in units of newtons times meters. We often just call it Newton meters. And literally it's just newtons times meters. Doesn't have its own unique name, but at least the unit we gave it makes sense, in my opinion. Now, what would happen if you doubled the length of the wrench and still apply 12 newtons on the end of it?
Just have a bigger torque.
You'd have more torque. And so a wrench with a longer handle, even if you are doing using the same amount of force with your arm, you're going to generate more torque, and that means the bolt is going to spin more easily just because the wrench had a longer handle. Again, if you use a smaller wrench or even just your bare fingers, that's less torque because of the smaller radius, and therefore it's a bigger pain. It takes more force to accomplish the same task. Most human tools, and surprisingly sports equipment, use this principle. Because what is a baseball bat but a lever arm so that you hit the ball some distance away from your knuckles? Would baseball be nearly as, well, could you hit the ball nearly as far if you punched it out of the air?
No.
No. For one, you'd hurt yourself. Two, you'd just be applying the force directly onto the baseball. But with the help of the bat, you're generating torque by the length of the bat itself. So that actually kind of ends up multiplying your effort. You are using torque instead of just straight linear force. Baseball bats, tennis rackets, golf clubs, crowbars, screwdrivers even, all tools designed to generate torque by giving you a bigger lever arm, a bigger radius to act on. There's an old quote attributed to Newton that says if you had a lever arm long enough, you could move the earth. Like if you had, a 2 million kilometer long wrench, you could theoretically push the earth around. Of course, that object would have its own gravity, and you'd be, at that point, living on it, but still, it's theoretically possible. So, torque's kind of neat, and you really do use it every day. I mean it. So, is this one sounding all right conceptually? Just kind of unlocking that layer that you already had in your brain? All right. Now, there are a couple quirks to torque that I want to make sure you're aware of. First, I'm going to back up and look at the formula again. Note that we've got this perpendicular sign again. We've got a few formulas with this so far. Actually, it's probably the first one with a perpendicular sign in it, come to think of it. We've got a few with a parallel sign. This one has to be perpendicular though, because the force has to be perpendicular to the radius that you are acting on. Now look at this wrench again. The radius here is horizontal, it's within the x-axis. If you were going to physically grab this wrench to try to make that bolt spin, what direction would you think to put the force in? Which direction would you push? Down or up, down or up, just kind of depending. If I hold this straight down, note that that force is perpendicular to the radius. And the same would be true if I pushed up. However, if I instead grabbed this wrench and pulled this way to the left, will that ever make the bolt spin? No, that's just going to remove the wrench from the bolt. Alternatively, if I grab the wrench and shove rightward, is that ever going to make the bolt spin? Also, no, that's just going to physically try to dig the wrench into the bolt, and that's not going to accomplish anything. to correctly generate torque, the force has to be perpendicular to the radius. And you can also see this with bike tires. Where I'm placing my hand, note that the radius is similarly within the x-axis. If I want to make the tire spin, I have to push either up or down, perpendicular to that radius. If I push leftwards, it's not spinning. If I pull rightwards, it's not spinning. Same with the door too. If this is the radius, I'm going to push either this way or this way. If I pull out this way, the door's not spinning. I'm just going to embarrass myself. Same if I do this. So that's why that symbol's there. The force and the radius have to be perpendicular to one another. Which means you can sometimes end up in some weird scenarios if the force isn't totally perpendicular. This wrench will spin. Whoever's using it just isn't using it very effectively. It's still a 1 meter long wrench, and we're still going to apply 12 newtons to it. However, that force is not completely perpendicular. It's now sitting at a 50-degree angle, which means the only part of that force that is going to generate torque, if I flash back briefly, is the portion of that force that is perpendicular to the wrench. So one would have to use a small bit of trig to figure out that leg of the triangle, that leg that is perpendicular to the length of the wrench. The portion that is parallel to the length of the wrench will never generate torque. It's just kind of pointlessly digging the wrench physically into the bolt. So in this case, instead of the full 12, sine of 50 equals force perpendicular over the total force. So force perpendicular is 12 times sine of 50. Force perpendicular 9.92 newtons. And so that force times the length of 1 meter would generate the torque. By changing the angle, you have reduced the torque by about 3 newton meters. So this is just not nearly as effective as if you were exerting all of the force perpendicular to the wrench. So, practical tip if you are ever using tools for such a purpose, always try to exert the force perpendicularly to the length of the handle. Technically the same is true for sports equipment as well, baseball bats, tennis rackets, golf clubs. Yeah?
Did you always use sine for that?
The way that I drew this picture, it wound up being sine because sine opposite hypotenuse. Hypothetically, if I drew it like this, it would switch. Of course, that would be 30 degrees. But it's always worth looking at the picture and not just assuming that y or perpendicular is going to come from sine. Because in this angle, sine opposite over hypotenuse, opposite winds up being this leg. So, tiny bit of trig refresher for the second test. Just a tiny bit. So, general rule, force always has to be perpendicular to the radius in order to generate torque. Questions so far? Bless you. All right. The other quirk of torque that I want to talk about today is another comparison of torque back to normal linear force. If you recall, if net force equals 0, an object is in equilibrium and not accelerating, correct? Net force equals 0, acceleration is 0, equilibrium, no acceleration. The same can be said of torque. If all of the torques on something add up to 0, that means that the object is in rotational equilibrium and it will not angularly accelerate. Right now, the door to this room is not angularly accelerating. It's not currently spinning, nor is that fact going to change on its own. Therefore, this door is currently in rotational equilibrium. It's not accelerating. That means that the net torque on the door must currently be 0. That changes if I come along and imbalance the system by adding in more torque. That then causes it to spin. If an object is angularly accelerating, then the net torque must be imbalanced. And kind of like how normal linear forces can all point different directions and add up to 0, the same is true for torque. The weird thing about torque, though, is whereas force can point in a bunch of different linear directions, torque only really has 2 options for vector direction. Those being clockwise and counterclockwise. Because those are the only 2 directions something can really spin. Clockwise or counterclockwise. Bless you. For that reason, there's only really 2 directions of angular acceleration, and as a result, only 2 directions for torque. If something is currently in rotational equilibrium, if all the torques are adding up to 0, that means all the clockwise torques are adding together with and canceling out with the counterclockwise torques. Which would imply that the sum of the clockwise torques equals the sum of the counterclockwise torques. All of the forces trying to make something spin leftward have to cancel out with all the forces trying to make it spin rightward if it is meant to stay in place. Now, this is the main thing I wanted to look at for lab this week, because lab this week is about seesaws, teeter totters. I mentioned that torque is everywhere, and that apparently includes children's playground equipment. When a kid sits on a teeter-totter, note that they're sitting some distance away from a fulcrum, and the force that they exert is actually perpendicular to the length of that fulcrum, because right now the teeter-totter is oriented horizontally and gravity points down. So when you sit on a teeter-totter, radius, perpendicular force, that's why it rotates, if it is imbalanced. If the teeter-totter is imbalanced, it rotates. But at least when I was a kid, me and my cousins would all play this game of trying to keep it as level as possible. Does that sound familiar? I'm not the only one. Okay. Now, if you did ever play that game, you might have realized that it wasn't always as simple as just one kid sitting on either side, because, you know, different people weigh different amounts, and therefore the forces on either side are different and generate different amounts of torque. So you might have had to find 2 kids that had the same mass, or maybe have someone stand on it at a weird halfway point in order to get all the torques to level out. Does that sound kind of familiar? Okay, at least one person is nodding. Two people. I'm not the only one. For this to work, the torques generated by each child have to cancel out. The kid on the right is generating clockwise torque because of their weight at this radius. The kid on the left is going to generate counterclockwise torque. fact that they're sitting on the other side means their force is going to try to make it spin in the opposite direction. So this kid's torque will be clockwise facing, this kid's torque will be counterclockwise facing. And in order for the seesaw to be balanced, for it to be stationary in rotational equilibrium, all of those, well, the counterclockwise torque and the clockwise torque have to cancel out. And we can actually figure out where each kid needs to sit to make that happen. Because they can't really change their mass. That's the amount of matter in your body. You can't change that. But you can change where you sit. So in this case, we have two kids. One has a mass of 30 kilograms. The other has a mass of 60 kilograms. The 60 kilogram kid is going to sit 1 meter away from the fulcrum. And we need to figure out where kid 2 needs to sit to generate the same amount of torque in the opposite direction, such that the net torque on the seesaw is 0. They are playing the game of trying to keep it balanced. Kid 2 has to figure out where to sit to make that happen. So, we need to add up all the clockwise torques and set them against the sum of all the counterclockwise torques, make sure they're even, and figure out where kid 2 has to sit so that is true. The kid on the right side is generating the clockwise torque, so we have to figure out how much torque they are creating. Once again, the formula for torque is radius times force. And there's only one kid on each side, so there's not really much to add. If there was 2 kids on one side, there'd be 2 torques on one side. Right now it's just 1 on each. On the clockwise side, we've got the 60 kilogram kid sitting 1 meter away. So that's our radius. That's radius 1. Now, how much force would this kid be exerting as they sit on the slide, on the teeter-totter? Right. The force they're exerting is basically their weight. If you sit on something, you're going to push down on it based on your weight. So, and technically this is the clockwise side. And you know what? I'm going to make an executive decision here, actually. You know, what goes on what side doesn't really matter as long as they're even to each other. I'm making this counterclockwise because the left sitting kid is generating the counterclockwise torque and the right sitting kid is generating clockwise torque. So I'm just going to keep them the same orientation as on the teeter-totter. So that means that the 60 kilogram kid is on this side. So on that side we've got radius of 1 meter. The force they're exerting is equal to their weight. So their mass times 9.8. On the other kid's side, we don't know where they're sitting or where they need to sit, but we can also find what their weight is. And so, by balancing the torque each kid creates, we can figure out where kid 1 needs to sit to balance out the seesaw. Now, by definition, gravity is a negative number. 9.8 is negative. But if we include the negative, it would just kind of cancel out on both sides. Frankly, in general, the 9.8 just kind of cancels out on both sides because it's all multiplied into each other. So whether you include it or not, it's just going to go away eventually. So to look at what doesn't cancel out, we've got R1 times 30 equals 60. Therefore, R1 equals 60 over 30. So kid 1, the leftward kid, has to sit 2 meters away from the fulcrum, whereas kid 1 sits 1 meter away from the fulcrum. By sitting twice as far away, they double the torque that their weight creates, and the teeter-totter and balance. Lab this week is a bunch of this, except instead of literal playground teeter-totters, it's meter sticks bouncing very precariously on a center point. So make sure to bring these notes whenever you show up to lab. Any questions for right now? All right, let me know if you need anything, and have a great day. Yes. At the end of the semester, I always give out a makeup lab, which is if you missed one, you can do this extra assignment for every grade.
Okay, so I'm not be able to make this lab, so I can do that here. Okay, do I should I email you guys to remember what?
I post the assignment at the end, and anyone who needs it. Thanks.
Good.
So these two objects are this far apart.